I'm going to be talking about some of the experiments we've been doing on two-dimensional superfluids at Queensland and looking at vortex clusters in those systems. And here we go. So just to briefly outline what I'll talk about, I'll again refresh your memory on point vortices, even though you've seen quite a bit of this afternoon. I'll talk a little bit about our experiment, also using these digital microwave devices to configure and stir BECs. And then I'll talk about some of our experimental results, the main one being observing clustered vortex states in a neutral vortex system. Pointing out the work of Chris Hummerson's group that was talked about earlier, where they looked at part of the phase space, I suppose, of these vortex states, and I'll be concentrating on the high energy states that you can see, it turns out, in experimental systems. And then finally, I'll be discussing some of our more recent and somewhat preliminary work on looking at what's called a chiral cluster of vortices. So that's a single sign cluster of vortices, and really showing that we can start looking at the equilibration dynamics of vortices in these systems. So I thought I should start out, instead of doing this at the end, to acknowledge the people who've contributed all this work, especially since I'll be showing quite a bit of their work, and especially these three people, including Matt Reeves, who's here in the audience, but then Guillaume, who's a PhD student of mine, and Quan, who's doing honors, which is the equivalent of masters. And the rest of the group at UQ, and then also our theory collaborators at the University of Otago in New Zealand, and of course all the funding. So just recalling vortices in these flattened BECs, we really can start to think about these as being two-dimensional vortices. And even though our systems are perhaps small on the scale of the helium systems that we've heard about some today, they're large enough that the core size is sort of on the order of 100 times smaller than the system size. And so if we forget about the superfluid, we can start thinking about these as just a system of point vortices. And we've all seen this in the previous talks. The velocity field for a point vortex just has this 1 on R character to it. And then the energy associated with the vortices is just given by this logarithm of their separation. And that only depends on the positions of the vortices within the system. So Onsager, of course, in this famous paper in 1949, talked about how high energy vortex states in the system are characterized by persistent clusters. And this has sort of been influential for a whole range of two-dimensional systems. Going into some more of the detail, and apologies to Tapio because I've got the equations in motion, which you just crossed one of those out. But the main point here is that because each vortex is carried by the flow of all the other vortices, essentially everything in the system only depends on the positions of the vortices. And so if you have a closed system, that means that the phase space of the system is also bounded. And if we take the entropy as the logarithm of some density of states, that entropy will also be bounded. And so to put this in a bit more context, and I'm showing here a calculation done by Matt Reeves, where I'm setting up my system, which is this, pointer's dead, but this elliptical system here, where I've got a neutral system of vortices, 18 in total, and then I'm just throwing those down at random, doing a microcanonical Monte Carlo calculation. If I do that 1 billion times, then I end up with a density of states from which I can just calculate the entropy. And the key thing here is that there's a maximum entropy, which turns out to not be at the maximum energy. And so there's this other parameter, which is important for my talk, called the dipole moment, which is just defined as this function here. So this, the sign of the vortex and its position, and it's summing over all the vortices of the system. And this dipole moment at this critical temperature or critical energy starts growing from 0. And this characterizes the transition for the vortex system to having persistent clusters. And in this case, these are clusters along the x direction, so they're separating along the long axis of my ellipse.
excuse me.
Yep.
On the horizontal axis, what is EM?
Sorry, EM is the it's just the energy of the peak. So this is not normally 0, but just for the sake of presentation, we shifted the energies so that the maximum entropy state corresponds to equals 0. So
this horizontal axis is an energy. Why did you?
Energy per it's energy per vortex. I think it was just for the sake of clarity in presenting it, so that this yeah, it's really an arbitrary choice. You could set EM equal to 0, and then that peak is a non-zero energy. So why do we care about actually looking for these vortex clusters? Well, they're long-lived states of the system with high vortex energy, assuming that there's decoupling from the other degrees of freedom in the system. So that's interesting from a non-equilibrium perspective. It's kind of a toy model, but it's been important for many different things. But the directly observing these sort of states hadn't been done before. 2D BEC superfluids, GP has shown that these behave very close to point vortex dynamics. So this is a great candidate system. And so our open question as experimentalists was, can we observe the full spectrum you expect from looking at point vortices in BECs? And these open questions about, what about the coupling to other degrees of freedom, like sound and system? We don't have a pure condensate, so there's some damping from thermal atoms. How are the equilibration time scales related to the hold times of our experiment, et cetera? These are all things that would be quite difficult to predict a priori. And then also there's a technical aspect of just trying to improve the control that we have over condensates to build on this line of research. So just to briefly talk about our experimental setup, and this is very similar to what Chris was mentioning earlier. So we have our atoms confined to a light sheet, which then compresses them vertically. And then on top of that, we project a pattern, which is a binary image uploaded onto a digital micromirror device. Here's a picture of what that looks like in the plane of the atoms. And then after some evaporation details, which are only interesting to the experimentalist audience, so I'll skip that, we end up with condensate filling the holes in that potential. So this is looking from the top down, which is most of the image that I'll show. If you look from the side, you'd see a very thin sheet because the Thomas Fermi, the ratio of the Thomas Fermi radii is around 20 to 1. And so the key thing is that these DMDs allow you to do dynamic potentials. You can also do some more exotic things like creating smooth potentials. And just to show off some pretty pictures, we're working currently on trying to make these kind of grayscale potentials by iterating on the atom density. And so this essentially means you can make art with superfluids. And so here's a picture of the Mona Lisa rendered with superfluid, which looks pretty good, except for it seems to completely destroy the subtlety in the smile. And you can have even more fun. You can make a BEC for each channel and make color images. And naturally, we have pictures of people in the lab rendered with BECs now. So actually using this potential for doing something with turbulence means going back to the rather more boring binary potential where the BEC is just going to fill this hole. We took inspiration from this paper, the Newcastle group, Carlos on there, where if instead of stirring the BEC with a round barrier like you might do with a Gaussian beam, if you use an elliptically shaped barrier, you actually see that you start getting these clusters of vortices that already have some separation to them. And so you can actually, instead of bringing the barrier through the middle of the condensate, you can bring it from through the side. So this is just a schematic of what we do. And this ends up creating a single sign cluster off to the side in your ellipse. So I'm going to show now some GP simulations done by Reeves, where we compared two techniques to try and inject vortices with different energy. So one of these was what we call the paddle stir. So this is now two paddles going through GP simulation here, showing that you get these clusters of vortices. that come off. And then low energy injection is to send a grid through the condensate. And you can see that the system here is now dominated by dipoles, which Chris mentioned earlier was a very low energy configuration for the vortices. So here's some images of what that looks like in our from the actual experimental images. So in situ images showing the barriers go through, and it's a little hard to see on this projector, more so than it is on my screen, but hopefully you can see that there's two clusters here, and then there's a random arrangement of vortices here. And these are the GP results showing the flow lines that you get from that. So if these correspond to what was predicted from the equilibrium dynamics for Onsager vortices, we expect that these clusters will stick around, assuming there's not coupling to other degrees of freedom in the system. We'd expect, because they're stuck in these clusters, they never actually touch each other, so there's no annihilation. And then when we map this system to point vortices, we'll see that we're far out in this high energy region. So to see whether the clusters are persistent, we can just take hold times up to 10 seconds, look at the histogram of vortex positions at 1 second intervals, and then at each second we have 10 images. So there's 100 images total spanning over 10 seconds here. And you can see that there's two persistent clusters that are apparent. And contrasting this with the grid case, where you end up with a relatively uniform distribution, meaning the vortices are freely wandering through the system. So this dynamic spatial non-uniformity is actually turns out to be a key feature of these states. And I should point out, the simulation here actually allows you to look at the vorticity, because this is an unsigned measure, just looking at the vortex density. And so just to put some actual numbers to that, here's the vortex number as a function of time, and blue is for the paddle case, where you have the clusters, and vortex number is essentially unchanged over the 10-second hold time, whereas the grid case decreases. And the solid lines are damp GP simulations. Another measure of whether the vortices are close to each other is this nearest neighbor distance, which you can see is much smaller for the paddle case, but then it gradually grows. And so this is indicating that there's some dynamics going on in the system nonetheless. So in order to talk about that a bit further, we actually can look at the energy of the system of vortices as given just by point vortices. Because we have this segregation clearly, and from the GP and the method by which we're stirring, we can just draw a line down the middle and then assign the signs across the axis. There's a little bit involved in trying to find out the energy of this system by using a map, a conformal map, to take the system onto a disk, where you can actually easily calculate the point vortex energy. If you're curious about the details of that, we also have an archive paper on this, which I've listed there. And so the results of doing that energy analysis are shown here. So the diamonds are the experimental points. The solid lines are the simulations. And just for a reminder, here was the plot from from my early slides, where this dipole transition is happening around 0.75 or so in these energy units. Apologies for cutting off energy units on the axis. You can see that we're starting quite far out into this region. So 8 versus 3 at the edge of this graph. And that's apparent as well in the measured dipole moment from the experiment and GP simulations. One of the things that you probably obviously noticed is that, of course, energy is rapidly decreasing with time. And so towards the end of the simulation, we're still above that transition, or end of evolution, we're still above the transition, but approaching that. And if you're curious about the sign detection, so this is, again, not actually detecting the signs directly, but we did do the same sort of Bragg sign detection that Chris talked about earlier, where you use the Doppler sensitivity of Bragg scattering The raw signal is shown there. That gives you this differential signal. And it does, in fact, turn out that the only configuration that matches the differential signal is one that has fully polarized clusters. Another argument for why why these must be clusters of the same sign is actually if you just look at point vortex dynamics and start changing the signs of one of these vortices, only changing a few signs actually drives you eventually into a histogram, which is going to look uniform. So there's this intimate tie between the high vortex energy and having spatial non-uniformity in these systems. What's causing the damping? Well, the most obvious things seem to be thermal damping due to the non-unity BEC fraction. And so we changed the temperature of the system, looked at the rate of the nearest neighbor decay, and saw that there was a relatively clear dependence. As you decrease the condensate fraction, the decay time decreases. So that seems to be our dominant source of this damping.
When you say decay time of what? Of the polarization?
This is of the nearest neighbor distance towards a value. So the value 1 here corresponds to just a uniformly distributed vortices on the ellipse. So it's again essentially just saying that the spatial segregation is the measure of this state. We also were curious about the role. So we have a relatively uniform gas, but we can actually make it less uniform just by making the trap larger. And so we looked at this effect. This is the nearest neighbor decays again, which actually doesn't seem to show much. So this is kind of interesting. This is all done with a high condensate fraction. The way that we measure the energy here is perhaps not working so well because this kind of disagrees with this other measurement. And so just speculating here as maybe this is a direction for future work is that even though we've been looking at this dipole state, I thought it was worth bringing attention to that there are other configurations for vortices in these systems, especially when you have a non-circular system known as this monopole state, which actually has a higher entropy. And so you would actually expect that the system would end up in this state eventually. So this might be an area for future work. All right, so with my remaining time, I'd like to now talk about this other experiment, which approaches these ideas of equilibration time in the presence of all this energy damping, right? So I mean, we should remember that the Onsager's picture is assuming that you have equilibrium between the vortices to actually have these states. So can we actually see whether we're remaining close to these equilibrium or quasi-equilibrium states, even in the presence of this energy damping? And so our approach for investigating that is to, instead of having the neutral system, work with this chiral system. And so this is a bit different in that because you only have vortices of one sign of circulation, well, first of all, the whole system is going to be rotating. So that's the fluid angular momentum here. And you won't have any vortex annihilation. You can, of course, still lose vortices through the edge of your condensate as damping occurs. This fluid angular momentum is maximized, say if you had a single vortex in the middle, and then as you move that out, this term, which you might be more familiar with from the point vortex literature, is point vortex angular momentum, is actually 0 at the middle and then maximized on the edges. I'm only pointing this out because it's often it was a source of confusion for me when first encountering this in the literature. And so what are the equilibria of the system? Well, you might recall from three-dimensional BEC work that when you have a bunch of vortices in your system, you'll end up with a lattice. Actually, I'll just skip through because I want to show this mean field analysis. So this is taken from this paper from Smith and O'Neill in 1990, where they looked at the system. And if you do the mean field analysis of this chiral vortex system, there's actually a quite interesting phase space where most of the states that you get are actually things that look like this blue spot here. So it's an off-axis equilibrium state. Whereas the ones that are axisymmetric only occupy these red parts of this plot. You can do the same microcanonical Monte Carlo again. You again see that there's a curve, which is an entropy curve, which is reminiscent of what we saw in the neutral case. It's a little difficult to do the Monte Carlo out in this region. I won't talk about the details of that, mainly because one of the things that we have to consider now is that we have two conserved quantities. So that's energy and angular momentum. Of course, those were conserved before, but the angular momentum was equal to 0 for the neutral case. So there's a little bit of subtlety here. So again, this different system, the chiral system, allows us to get at these remaining questions from my introductory slide. And so our experimental approach was to adapt our DMD stirring procedures. First of all, just to produce states close to the two classes of equilibria. So this is conceptually similar to what we were doing in the neutral case, where we put in these clusters which rapidly thermalize to something which is like the Onsager Vortex neutral case. But then also trying to produce one of these off-axis clusters as well as a central one. And then to create an initial state which is actually not in equilibrium, and then examine the dynamics of the system and whether it attains one of these equilibrium states as predicted by the Monte Carlo theory. The technical details of this, okay, well, I already showed the side sweep, so this produces a cluster off-axis. So, you know, right from the start, this has a non-zero initial dipole moment. To produce a cluster on axis, experimentally, this is actually a little bit trickier than it might sound. We took the approach of actually producing a persistent current in an annular trap, and then you can remove the middle of the annular trap, and you have you know, a very tightly bound cluster left in the condensate. And so that's seen here as this big hole. It's actually so high energy that we have to wait for the vortex damping to reduce the energy and spread out the cluster so we can actually count the individual vortices. And so here's an image after a few hundred milliseconds of evolution, and you can now see that you could actually identify the vortices there. So that very consistently gives you a cluster in the middle of your condensate. In order to inject a non-equilibrium configuration of T-like signs, this is essentially the same as a double paddle technique, but now one of them goes the opposite direction. And so this gives you both high energy and a large point vortex angular momentum. And so this should very much be in that blue region of the mean field diagram. So here's the actual experimental histograms. Just details on this. So there's 250 milliseconds between frames in my animations here, up to a little less than 7 seconds total. There's quite a lot of data in there, and these are all you know, destructive images. So essentially some ensemble averaging going on, which we'll see the effect of that in a second. But first of all, just for the central cluster case, you can see it just kind of parks around the center. The red dot is the dipole moment. And as time evolves, the cluster just spreads out in area. For the off-axis case, if we just look at the raw histograms, you can see that this thing processes around like we expect, but then it kind of rapidly sort of blurs out into this big ring of vortices. And so that's due to this ensemble averaging. Essentially, there's some shot-to-shot fluctuation in the rotation rate. So the way to fix that is like, well, let's just rotate the dipole moment so that it lies along the x-axis. And you can see now that we have you know, a fairly well-defined cluster that, again, just grows in area as the evolution continues. And now for the non-equilibrium initial condition, the non-rotated case quickly becomes kind of a mess. But now if we look at the rotated case after some amount of time, you can see that the red dot is no longer in the middle, and it looks like we've ended up in one of these situations. So the preliminary approach to modeling this is actually just to do point vortex modeling. And this is the work of Matt Reeves. That's much better. This is just, so the motion of or the velocity of an individual vortex is just given by the velocity of the rest of them. But then it's modified by having this Brownian motion type diffusion term, where this is essentially just a fitting parameter with some Gaussian distributed variation. So that's calculated for each vortex and each time step. And so the results showing here the vortex number, where the center case is red, the double paddle is the green one, the single paddle is the blue one. The point vortex modeling is shown with solid lines. There's two different temperatures. The temperatures used are slightly different. That's essentially what was just needed to actually fit the data, but we don't necessarily think that's unreasonable given that the mechanism for stirring in the center vortex is actually quite a bit more violent, perhaps, to the condensate because you're removing that barrier from the middle. And if you're wondering why the vortex number jumps up, this is just this effect that I showed earlier where, when the cluster is so tightly bound, we can't actually resolve the individual vortices in it. And so we can again look at the point vortex energy, and this all seems to agree quite well as well. You can see that the center cluster is certainly the most energetic situation.
And so at short times, you have this rise of the vortex energy.
Yeah, that's actually again just an artifact of the measurement. So that's just an artifact of not being able to actually identify. It's just our algorithm that looks at the images and identifies the vortices if they're all grouped together where we can't distinguish them. Yeah, that's right. And so here's the results for the dipole moment as a function of time and the angular momentum as a function of time. As you might expect, the center pin doesn't have much of a dipole moment. It's quite close to zero. The off-axis one has a large dipole moment, which gradually decreases as the energy damping takes over. But the interesting one is this double paddle case. And then it starts essentially at this the same value as the center pin case, but then rapidly jumps up to this non-zero value and then gradually tracks down. And you can take the energy vortex number and angular momentum for each of the experimental points, and then do this Monte Carlo approach, which is this approach called annealing, where you take a random distribution of vortices, and then you essentially just let them do random walks until they end up within the window of this E and M. And you do that enough times so you get an ensemble that allows you to calculate the average dipole moment. And the encouraging thing here is that, at early times, the energy and angular momentum that we put into the system absolutely don't correspond to one of the equilibrium cases that you'd expect from the Monte Carlo. But then when it jumps up to this line here, there's quite good agreement. And so another way of looking at that is to just fix angular momentum, even though it varies by about 10% through the evolution of the system. And so then we can see what the dipole moment should be as a function of energy. And you can see that the initial condition corresponding to this is pretty far from that line, but then essentially just tracks up to it. And then even as the energy is damped away from the system, the experiment tracks down what you expect from the Monte Carlo results. So I actually went a bit faster than I anticipated, but I'll just summarize there. So I talked about our observations of Onsager's vortex clusters. We're pretty pleased with that result, and especially the control we have, and also identifying some of these experimental constraints that are important for these experiments. I didn't mention that we do have some BEC number loss, so that turns out to not be the dominant damping mechanism. Instead, this is related to the temperature of the system. And then kind of an open question from that experiment was this question about whether we were actually in equilibrium or not in the presence of this energy damping. And the chiral clusters case, I think, demonstrates that quite nicely. And so some of the future directions we might take, first of all, we already been able to get into this very high energy cluster regime through the initial condition for that center pinned case that I showed. So there's probably some interesting things to study there. This is a prototype for perhaps more complex initial conditions. If anybody was here for the workshop last week and heard Thomas Kazenzer talk, his initial conditions were arrays of vortex clusters. So that's a possibility. And another direction is to try and increase the size of the condensate further to be able to fit more vortices in it and actually have a larger ratio of intervortex distance to the system size, or smaller ratio, to try and look at some of these other cascades, which actually perhaps appears that it could be feasible with some changes to the experiment. Before I stop, I should mention, since I'm on the committee for this Cleo Pacific Rim conference, if you're interested in coming to visit Australia, keep an eye out for that next year. There is a atomic physics component to that. And I'll just stop there and say thanks for your attention and show off our BEC squared. So, thank you.
Thank you. Any questions?
Yeah.
Can you show the post-model just last one?
This one?
Yeah.
Yeah.
Yeah. So it looks like that equation there where you've got the fitting parameters, temperature, T, that term there is nothing but the density gradient term. And I think you could actually measure it directly from your experiment, because you can see the fluctuations, the density, so just measure it directly.
Yeah, I guess I see what you're saying.
That's the Vortex equation of motion. And the second term is the density gradient, the third one is the phase gradient. You can actually measure it explicitly from your experimental data.
Well, we did kind of distinguish between the role of density gradients and temperature in the previous experiment, though. Sorry, the overall temperature of the system. So I do think that, I mean, you still will have that decay due to the BEC fraction being 80% here, right?
Yeah, that's basically the fluctuating density of the phonons and stuff.
Okay, that's weird.
But what I'm saying is that you can actually measure it rather than using it as a fitting parameter.
Yeah, okay, I'll have to think about that.
Sure, these are phase fluctuations, because the density is a grad log of density, right? So you get a noise term from the phase fluctuations. You know that. More important. But I agree. I think that's
exactly.
Yeah, okay.
It's just that. So I thought about doing PGE.
Yeah, sure. I should have mentioned that. That would be the most rigorous way of doing this. Sorry, Arlen, you had to.
Certainly this equation is here, and I don't understand it. If it's Brownian motion, you should have dissipation and fluctuation. I see only fluctuating term. This is one thing. Secondly, it's not clear to me what the temperature is there, because it's not the temperature of the vortex cluster, which is negative, so then the square root of T doesn't make any sense. So what's the temperature there? And
right.
the next aspect is this Brownian motion should drive the system to equilibrium. And you'd expect your equilibrium, you should be at negative absolute temperature, which I don't see how this would work.
Well, I guess, yeah, sure. I think it's really trying to just kind of phenomenologically model the fact that you ought to be doing something like SPGP to actually account for the fluctuations coming from the external system. So I should mention maybe it's a
temperature here is temperature of what?
Well, I'm not sure if it's very physical.
T is not temperature.
It's not really temperature. It's just.
I'm sorry.
It's not that T is not temperature.
We probably should use something other than.
Depend on the temperature, but at the moment it's just.
Yeah, it's just a fitting
You don't have dissipation, you have only fluctuation.
Yeah,
You have
so
dissipation.
I did actually try having various approaches. So like the first approach was just applying mutual friction.
I'm sorry, say it again.
So the first approach I tried was just using mutual friction, like what Carlo talked about, and we couldn't get it to agree with the experimental data. And then I tried what you'd expect from fluctuation dissipation, and that also did not agree with the data. But for whatever reason, doing this alone does. We don't really understand why this agrees at the moment.
I should just one comment there was that the actual equilibrium for the system as a whole is, of course, just a BEC that has no vortices in it. So there's kind of two different things here. It's, Chris mentioned this as well, right? We're sort of thinking about the vortices as being an isolated subsystem within the BEC. That finds its own equilibrium.
You seem to do only that here, so I don't
Yeah,
understand
okay.
your modeling. So what will be the solution of this equation? It will be equilibrium of what in one system? What will be the path?
Yeah, okay. We'll have to think about that a bit more. All right.
Okay, thank you very much. Let's take a 2-minute break and let the people who are coming in for the special seminar move in to the center of the room while we get set up here.